Imagine you are looking at a cloud. It's not a solid thing, is it? It has no clear edge. It's just a fuzzy, swirling collection of water vapor. You can't really say where the cloud begins and where the empty sky takes over. Now imagine if everything in the universe wasn't made of tiny, solid billiard balls like we usually think. What if instead, some parts of reality were made of something more like that cloud? Something without a definite shape or size. This is the strange and wonderful idea behind a concept called unparticles. They are not particles in the traditional sense. They are something else entirely. A kind of cosmic fuzz that might be hiding just out of sight, woven into the fabric of space and time itself. We are all familiar with the building blocks of our world. We learn about them in school. Atoms are made of protons, neutrons, and electrons. These are particles. You can count them. 1 electron, 2 electrons. You can measure their properties, like their mass or their electrical charge. Think of them like Lego bricks. You can click them together to build something bigger, but each brick is a distinct, solid object. You always have a whole number of bricks, never 2.5. Think of it like a ripple spreading across a pond. You can't say you have 1 ripple or 2 ripples in the same way you can count stones. The ripple is a pattern of energy that exists over an area. It doesn't have a fixed mass. In fact, it doesn't behave like it has a single mass at all. It acts as if it has a whole range of masses at the same time. So how can something have no mass, no charge, no anything we can easily pin down? It sounds impossible. Our entire physical world is defined by these properties. A particle without them is like a ghost. It's there, but it's not. It can pass through walls, so to speak, interacting so weakly with our world of matter that we would barely notice it. A single clear note from a flute is like a particle. It has a specific frequency, a definite pitch. An unparticle, on the other hand, is more like the sound of a huge crowd murmuring. It's not one single note. It's a blend of thousands of different sounds, a continuous spectrum of noise. One of the most mind-bending properties of unparticles is something called scale invariance. Think of a fractal like the classic Mandelbrot set or the intricate pattern of a snowflake. If you zoom into a tiny part of the fractal, what do you see? You see the same complex pattern repeating itself, just on a smaller scale. The structure looks the same regardless of your magnification level. This property, of looking the same at all scales, is what we mean by scale invariance. It's a kind of perfect, infinite self-similarity. This is the secret rule that governs the hidden world where unparticles might live. The theory of unparticles behaves as if it exists in a fractional number of dimensions. This sounds like pure science fiction, but it's a concrete mathematical outcome of scale invariance. A fractal coastline, for example, has a fractional dimension between 1 and 2. It's more complex and wiggly than a simple straight line, but it doesn't fully cover a flat area. An unparticle field is like that. Its presence fills space-time in a way that is more diffuse than a point-like particle, but less substantial than a field that uniformly fills all of space. So, where do unparticles come from? In modern physics, every particle is an excitation of a field. Think of the entire universe as being filled with invisible fields, like oceans stretching through all of space and time. There's an electron field, a photon field, a Higgs field, and so on. When you add a bit of energy to the electron field at a certain point, a ripple appears, and we perceive that ripple as an electron. The unparticle idea proposes the existence of a new kind of field, an unparticle field, with very different properties from all the others. It would be a perfectly smooth, featureless ocean, without the inherent lumpiness that defines the other fields. An excitation in this field wouldn't create a discrete particle-like ripple. Instead, it would create a diffuse, spreading disturbance, the unparticle pattern we've been discussing. Imagine 2 oceans lying next to each other, separated by a near-perfect barrier. One ocean is our universe, full of the waves we call particles. The other is the unparticle ocean. But Howard Georgi's idea was that perhaps there are tiny, microscopic holes in the barrier. Through these holes, energy could leak from our ocean into the unparticle ocean, and vice versa. In a very high-energy collision, like 2 protons smashing together at the LHC, we might pour enough energy into one spot to punch a temporary hole in the barrier. Some of that energy would spill into the unparticle field, creating one of these strange pattern-like excitations. Every great idea in science begins with a simple question. For unparticles, that question was asked by a brilliant physicist named Georgi. In 2007, working at Harvard University, Georgi was contemplating the grand landscape of particle physics. He saw the Standard Model, a towering achievement that described almost all known particles and forces with stunning precision. But he also saw its limitations, the cracks in its foundation where mysteries like dark matter, dark energy, and the hierarchy of particle masses slipped through. He wasn't trying to fix one specific crack. Instead, he decided to step back and ask a more fundamental question about the very nature of reality itself. Georgi's question was this: what if the building blocks of the universe aren't all particles? We assume that everything, at its most basic level, must be made of discrete, countable things. But why must this be true everywhere and for all forms of matter and energy? What if there exists a sector of reality that simply doesn't play by these rules? A corner of the cosmos where the fundamental constituents are not point-like objects, but something else entirely, something continuous and fuzzy. He published his thoughts in two groundbreaking papers, Unparticle Physics and Another Odd Thing About Unparticle Physics. The names themselves have a certain playful curiosity to them, hinting at the strangeness of the concept. Georgi wasn't claiming that unparticles definitely existed. He was performing a classic thought experiment, a what-if scenario pushed to its logical conclusion. Georgi's work laid out the mathematical framework for how these strange entities would behave, and crucially, how we might be able to detect them. He provided a new target for experimental physicists to aim at, a new and exotic possibility in the grand search for what lies beyond the Standard Model. The abstract world of theoretical physics is fascinating, but for an idea to truly matter, it must be testable. This is where the unparticle concept truly comes alive. It provides a concrete, albeit strange, new target for the most powerful scientific instrument ever built, the Large Hadron Collider at CERN. The LHC smashes protons together at nearly the speed of light, recreating the conditions of the early universe for a fraction of a second. In the debris of these cataclysmic collisions, physicists search for signs of new physics, and unparticles have a very specific, if weird, signature to look for. As we've discussed, most searches for new physics at the LHC involve looking for a bump in the data, a sharp peak at a specific energy that signals the creation of a new particle with a definite mass. But hunting for unparticles requires a complete change of strategy. The telltale sign of unparticle production would be what physicists call missing energy. If the collision creates an unparticle, that unparticle would slip away from the detector without a trace, carrying energy with it. From the experimenter's point of view, it would look as if some energy had simply vanished into thin air. This missing energy, combined with the observation of a broad, continuous spectrum in the remaining particles, would be the smoking gun for unparticle physics. This gives experimental physicists a new and exciting research program. It encourages them to analyze their data in novel ways, to look for these strange, non-resonant signals that might have been overlooked before. The hunt is on, and every collision at the LHC carries the potential to provide the first hint of this hidden, continuous reality. So why do physicists spend their time contemplating such a bizarre, ghostly concept? The primary reason unparticles matter is that they could offer elegant solutions to some of the deepest and most stubborn mysteries in modern physics. One of the greatest of these mysteries is dark matter. We see its gravitational effects everywhere. It holds galaxies together and shapes the large-scale structure of the universe, yet we have no idea what it is. All we know is that it makes up about 85% of the matter in the cosmos, and that it barely interacts with light or ordinary matter. Physicists have searched for decades for a particle that fits this description, but so far, they have found nothing. The unparticle idea provides a radical alternative. What if dark matter isn't made of particles at all? What if it's made of this strange, continuous unparticle stuff, a vast, diffuse cloud of it filling the universe? This is a tantalizing possibility. Because unparticles are electrically neutral and interact so weakly, they would be invisible and would pass through normal matter almost without a trace, just like dark matter is supposed to do. Their strange continuous nature could also explain why traditional searches for a single dark matter particle have failed. We've been looking for a needle, but perhaps we should have been looking for the haystack itself. Beyond dark matter, unparticles could also shed light on other puzzles, like the masses of neutrinos. Neutrinos are ghostly particles that have a tiny but non-zero mass, something the original Standard Model doesn't explain. The subtle, continuous influence of a hidden unparticle sector could provide a natural mechanism for giving neutrinos their slight heft. The unparticle's ghostly touch could slightly alter the properties of familiar particles in just the right way. In essence, unparticles matter because they are not just a curiosity. They are a potential tool, a new theoretical framework that could connect disparate problems and solve them not by adding another simple gear to the machine, but by revealing a whole new engine running silently in the background. Ultimately, the reason unparticles matter goes beyond solving specific problems or giving experimenters new things to hunt for. Their true importance lies in how they challenge our most fundamental assumptions about the nature of reality. For centuries, Western science has been built on a foundation of reductionism, the idea that you can understand complex systems by breaking them down into their smallest, simplest constituent parts. Unparticles smash that foundation. The theory suggests that reductionism has its limits. If you try to break down unparticle stuff, you don't find smaller, more fundamental bits. You just find more of the same continuous, scale-invariant substance. It is irreducible in a completely new way. This is a profound philosophical shift. It implies that to exist does not have to mean to be a discrete object. Something can exist as a pattern, a spectrum, or a continuous potentiality, woven into the fabric of space-time itself. This opens up entirely new ways of thinking about the cosmos. If a continuous, scale-invariant sector exists, could there be others? Could the universe be a patchwork of different realities, each with its own dimensional properties and physical laws, all weakly interacting with one another? The unparticle idea is the first plausible theoretical model for what such a connection might look like. It provides a mathematical language to describe the interface between a digital world of particles and an analog world of continuous fields. In the end, this is why unparticles capture the imagination. They represent the frontier of knowledge, the line where our familiar concepts break down and something new must take their place. They remind us that the universe is under no obligation to conform to our intuition. They matter because they are a powerful symbol of the unknown, a testament to the fact that there are still rules of reality left to be discovered, and that the next great breakthrough might not just break the rules, but rewrite the entire rulebook. If we were to wake up tomorrow to the news that physicists at CERN had found definitive proof of unparticles, it would be a moment that would reshape our entire picture of the cosmos. It would be as profound as the discovery that the Earth was not the center of the universe, or that matter was made of atoms. The first and most immediate implication would be the confirmation that our universe of particles is not the only game in town. It would mean that a hidden, parallel reality, governed by completely different physical laws, is not just a mathematical fantasy, but a tangible part of our existence. While the initial implications of discovering unparticles would be purely scientific, it's impossible not to speculate about the distant future. Could we ever harness the properties of this strange new reality for technological purposes? The unique properties of unparticles, like their lack of definite mass and their scale-invariant nature, might also open doors to manipulating space-time itself in new ways. Of course, the path from a fundamental discovery to a useful technology is long and uncertain. While we may never build an unparticle engine, the pursuit of that knowledge would undoubtedly change our world in countless ways, just as the pursuit of quantum mechanics gave us the computer. The story of science is a story of expanding horizons. We once thought the Earth was the center of all things, only to find we live on a small planet orbiting an ordinary star in a vast galaxy. This quest to understand the fundamental nature of existence is not just an academic exercise. It is a deeply human endeavor. It speaks to our innate curiosity, our desire to understand where we came from and what the universe is truly made of. Unparticles represent a frontier of pure possibility. They remind us that the world is full of wonders still waiting to be discovered, that there are ghosts we have yet to name, and that the story of our quest for knowledge is far, far from over. The universe is waiting, and we have only just begun to listen.